Welcome. In this video, we are going to discuss about the topic scintillation counter. Scintillation. The flash of light that is produced by a transparent material due to the passage of subatomic particles like electrons, ions, alpha particles or photons is called as scintillation. Scintillation counter is a device that is used to detect radiation by means of a scintillation effect. So we also call it as scintillation detector. Scintillation is a major part of a scintillation detector. This is the diagram of scintillation counter. So scintillation counter will has two major parts. One is scintillator and another one is photomultiplier tube. So the two major component of the scintillation detector is a scintillator and photo detector or photomultiplier tube. Let us see what is scintillator. A scintillator is a device that emits light when a high energy particle hits it. The energy of the emitted pulse of light is directly proportional to the particle that hits the scintillator. The generation of photons occurs in the scintillator as a response to the incident radiation. Let us look at the diagram of the scintillator. Scintillator, what it will do, it will generate the light photons for the incident particles. It may be a radiations or it may be electrons or ions or alpha particles or beta particles. So the scintillator finally it will generate the photons. Photodetector. A photodetector, what is the role of the photodetector? So it converts the light into an electrical signal in order to process the signal. A photomultiplier tube, so it is a photodiode, okay, or a charge coupled device, okay. These are all can be used as a photodetector. So let us see how this scintillation counter will works. When the ionizing incident radiation enters the scintillator, it interacts with the material of the scintillator, due to which the electrons enter an excited state. So the charged particles follow the path of the particle. So the energy of gamma radiation, so usually the gamma radiation is uncharged. So it's converted to a high energy electron either through the photoelectric effect or Compton scattering or pair production effect. So now the excited atoms of the scintillator material gradually undergo the de-excitation. During the de-excitation, it emits the photons in the visible region of the light. So this emission of the photon is directly proportional to the energy of the incident ionizing particle. So the material will get shines or flows brightly due to the fluorescence. So this is how the scintillator is working. So the pulse of light emitted by the scintillator will hit the photocathode. So where it is placed, the photocathode, it is placed in the photomultiplier tube. And this pulse of light emitted by the scintillator will hit the photocathode and it releases at most one photoelectron for each photon. So these electrons are accelerated through electrostatic means by applying a voltage potential and are targeted to hit the diodes. So we should have enough number of diodes in order to accelerate the electrons. So after that, these released electrons are called secondary electrons will strike the secondary diode. So thereby releasing further electrons. So this process is called as multiplication. Okay, multiplication of electrons. So this process occurs in the photomultiplier tube. So for each subsequent impact on the dynode will releases further electrons, and hence a current amplifying effect occurs on the dinodes. So each subsequent dynode will be maintained at a higher potential compared to the previous one. So it helps in enhancing the acceleration. Okay, in order to maintain each dinodes at higher potential when compared to the previous one, what it happens, it helps to maintain the acceleration. So the primary signal is multiplied throughout 10 to 12 stages in the photomultiplier. At the final dynode, highly sufficient number of electrons are present to produce a pulse of high magnitude to develop the amplification. So this pulse carries the information about the energy of the incident ionizing particle. The number of pulses per unit time gives the significance of the intensity of radiation. So look at how the photomultiplier tube is constructed. Okay, so it has a cathode, and each stages, okay, from plus 100 volt, next dynode is maintained at plus 200 volt, and next at plus 300 volt, and 400, 500, 600, 700 and 800 volt at the final dynode. First, the photons which is generated in the scintillators will strike at the cathode. Okay, and it takes the path of the electrons to the next higher potential from 100 volt dynode to 200 volt. There it get multiplies. You can look at how much electrons it get multiplied. After that, it will hit to the next higher potential dynode, that is 300 volt. Okay, we have to arrange the path like that. So next again it is getting multiplied. So the electrons are further it is getting multiplied, and finally will be collecting at the anode. So what are the materials which can be used for a scintillator? So the scintillator consists of a transparent crystal, so which is usually a phosphor, plastic or organic liquid that fluoresces when struck by the ionizing radiation. So generally it is classified as inorganic crystals or crystalline type scintillators, plastic, phosphorus or organic crystals. So inorganic scintillator. So these are all the crystals grown in high temperature furnaces like lithium iodide, sodium iodide, cesium iodide, zinc sulfide, and the most widely used scintillation material is thallium doped sodium iodide. This is specially used for gamma detectors. So these crystalline scintillators are characterized by high density, high atomic number, and the pulse decay times is approximately 1 microsecond. So the inorganic scintillators are better suitable for detecting gamma rays and X-rays when compared to the organic scintillators. The only disadvantage of the inorganic crystals of sodium iodide is it has a special property called hygroscopicity. So this property, what it makes is, we used to maintain this scintillator in a protected container in order to avoid the moisture. Next type is an organic scintillator. Organic scintillators will have a fast decay times, approximately 10 power minus 8 seconds. And the pure organic crystals like anthracene, stibbilene, naphthalene are used as an organic scintillators. So its decay time is approximately 10 nanoseconds. So this is better suitable for detection of the beta particles. Next is plastic scintillators. Plastic phosphorus are made by adding a scintillation chemicals is called as a plastic matrix. So it has a very short decay constant, nearly 1 or 2 nanoseconds. And the plastic scintillators are used as high flux environments. It is used in the environments and for high dose rate measurements. Okay. And the plastic has a high hydrogen content, so therefore it is useful for fast neutron detectors. Three conditions for plastic scintillators. So it is used in high flux environments, high dose rate measurements, and used for fast neutron detectors. Thank you. Thank you for watching.